and you have the 55-minute stretch, put in some minutes for just figuring out what the problems are asking you for, then you want to get through things as quickly as possible. So this is number 4 off the WebAssign. And this is the one Jason was working on yesterday.
Oh, yeah.
So step 1 is to always, like in all the most of the problems that you have, step 1 is to find the partial derivatives. So here it's just like your Calc 1 stuff. You take the derivative, set it equal to 0. So fx is 3x squared minus 6x minus 9. Fy is equal to 3y squared minus 18y. Set that equal to 0. One thing to watch for is that when you're setting these equal to 0, don't do it the old school way of factoring. We call this equation 1 and equation 2. So if you factor here, you'll get the y and the 3 out, and you get y minus 6 inside. If you don't do that, you might miss the 0. So you get one solution here, y equals 0, and the other solution, y equals 6. So that's you have to kind of watch out for that. When someone's creating a problem like this, especially for a test, they're thinking, if I put a 0 in there, it's going to make it easier for them. But in some ways, like you might, if you miss that, it's going to make it so that it's difficult for you to find some of these things. All right, so we have y equals 0, y equals 6. Now I have the top equation. It's a cooked problem from the textbook. So I can factor it. Is that correct? 3 minus 3. Let me not skip steps. Yep. So then I get x equals 3 and x equals minus 1. Now, what you do, because these were independent of each other, when I solved them, I didn't have to really depend on sticking one equation into another. So what I have to really do is lay out all the different possible answers I have, combinations. So I could have x is 3, y equals 0, x equals minus 1, y equals 0. So my critical points, you guys are used to acronyms, CPs. Critical points are 3, 0, minus 1, 0. Then I can also have minus a 3, 6, and then minus 1, 6. So I have 4 critical points. Next step is to calculate the Hessian matrix. They have the second derivative test in your book. It's the same thing as the determinant of the Hessian matrix. So it's the same guide. Everybody have this down? This is in the notes too if you're missing anything.
Do you have to plug all those critical points back into that first equation to make sure they all work though?
I don't think you'll have time to check your work.
Okay.
Yeah, I can't believe I'm saying that because I used to always tell students you have to say that. We had block scheduling too, so we'd have 3-hour classes, so you can give them a 3-hour test too. But I didn't. I looked at it as a set. If I have what I need from you, I just need to know that you know this. I was okay with giving them a 1-hour test in 3 hours at a time because I'm not for speed, but I'm told that you need to learn how to work with speed. And so some of the best officers here, they can think so quickly, and I love working with them for that skill. So it's a skill I think you need that Montclair State students probably don't. So the Hessian matrix. I erased my first derivatives. Here goes fxx. So you take the first derivative. If you have it on your page, it's 3x squared minus 6x minus 9. So you get 6x minus 6 over here. This fxy goes over here. There were no y's in the first derivative, so you get nothing. And if I was low on time, I would just do this. I wouldn't go check it. If I have time to check, I'll check. But I'm just going to assume that I'm right here. I just put a 0 there because these two should always be the same. And then fyy goes here. I get a 6y minus 18. And that's pretty nice because it means that whenever you have what's called a diagonal matrix, that means that you only have things on the diagonal. The eigenvalues are right on the diagonal. So don't actually go and solve any equations. Go as fast as you can. So now you pop in those critical points. H at 3, 0 is equal to, just put 3 in for x. I don't actually need to do anything. put in 0 for y. I just need the signs of those values on the corners. Positive, negative. Whenever the eigenvalues are of opposite signs, it's a saddle. So that's what I meant by tips. That's why I'm going through this with you guys to see like how to speed up how quickly you do the problems. Then you do the same exact thing for -1, 0. Following so far? It makes a difference, right, when you're just presenting it versus you're seeing it on a PowerPoint or something. So we did this one. If I put -1 in there, I get a negative number here, 0. If I put 0 in here, I get a negative number here. So both eigenvalues are negative. And if they're both negative, it's just like the second derivative being negative. So you have a concave up function. So this is going to be a both negative, concave down. You're right. I said it wrong. I put these in quotes because it's not really concave down, but it's an extension of that. So these, it's a local max. And then you reapply. You do this for every single one of them. So we got this one done. If I put 3 in there, tell me the sign.
Positive.
Positive, 0, 0, 6. Positive. So it's concave down in this case, so it's a local, concave up, so it's a local min. And you can't do this at your desk, but I can do this. Put an H in there. So if I get this, I just need the signs. I get a negative here, 0, 0, and positive here, another saddle.
So there's just because the like you can tell that you get a negative and positive when you plug the numbers in. How do you know that the eigenvalues are negative and positive? Because don't we have to subtract them if we're finding them?
Yeah, so let me show you what happens if you have, I think everybody's got this slide now, so. So if you have what's called a diagonal matrix, like so, then when you subtract lambdas off the diagonal, what you're going to get is A minus lambda times B minus lambda equals 0, and you just get lambdas A, lambdas B. So I don't really need to do this work. I can just pluck these. These are the eigenvalues, the A and the B. So I don't need to do extra.
So that only works when you've got zeros.
Right. Now, if you have zeros on the opposite side, so let's suppose you had zeros here, and here you had numbers. Like usually it's the same number because these mixed partials are exactly the same. So let's say you had D here. Then the determinant of A is going to subtract off lambdas. We're going to get lambda squared minus D squared. So your lambda is going to be plus or minus D. So if you just recognize that, the second you recognize that, you don't have to go through any more work. You'll know what those are. This most likely is always going to give you a saddle, right? You can see that here. The only case you won't get that is D equals 0, and then the test is inconclusive. You remember when the second derivative was 0, the test was inconclusive? The eigenvalues are all 0, the test is inconclusive. Clear? All right, there was one last, number 5 was a little tricky. I you what to do via the PDF, and then we're gonna, this one was due already, or is it due today? The max and min one. Tomorrow? So we'll get that resolved together in class. So do you remember the problems where you had to find a max or a min over an interval? So then you had to find the critical points in that interval, and then you had to find the values at the boundaries, and then you listed them in a table, and the biggest one was your max and the smallest one was your min. So here now, what can happen is you have a surface, you want to find the max or the min over surface over a region on the XY plane. The region that they give you in number 5 is a circle in the XY plane. And they want you to find the max and min, like of this umbrella thing on top, on that circle. Instead of an interval, you have a circle. And so you do the same process. You look for the bumps by finding the derivatives and setting them equal to 0, finding your critical points, and then you look along the boundary and plug that in, and then look at all the possible z values. The biggest one's your max, the smallest one's your min. It's a 3-dimensional version of what you did in Calc 1. So we'll go through that because I made it sound very easy, but it's not messy.